Okay, we're going to, today we're going to learn about changing from phasors to using complex numbers to represent phasors. Okay, if you recall, complex numbers are made of real parts and imaginary part. The imaginary part number is actually a number that's multiplied by the square root of -1. So we're basically in our PowerPoint presentation for day 2 gets into that, and we'll go over that. I'll try to take you step by step through that. So first, let's pick it up and let's view it as a slideshow. So it's basically we're giving information on chapter 24, complex math. We'll look at first the number system, how we got there to get to a complex number. Take a quick look at a complex plane. Then we'll get into what we're really interested in, complex numbers and AC circuits. We have to figure out what's the math involved. Okay, how do we manipulate complex numbers? And we're going to find out how we can actually use our calculator then to change from rectangular coordinates to polar coordinates. Okay, so basically that says that our complex numbers can be represented both as a rectangular system or as a polar coordinate system. And then we'll look at different circuits, how to resolve those. Simply, we started out with numbers 0 to infinity is a one-directional, and because we decided, well, there could be deficits as well. Now we got a one-dimensional, but it's goes both to positive and negative sides. So we created positive numbers and negative numbers. But then when we got into calculus and higher order math and tried to solve some really complex, really hard graphical solutions, we often get something that we have to resolve a solution for x squared equals -1. So basically, we don't know what the square root of a minus number is. So we call that an imaginary number. And so we're more interested in a two-dimensional system for electronics. So we will have the x and y axis go both in plus and minus directions, and but they will be represented by real and imaginary parts. All right. Commonly, if you recall your math, the complex number is given as a number of a plus bi, where a is the real portion, b is the imaginary portion, and I represents the square root of -1. But because we use I as current, we don't want to get mixed up in electronics. So in using the I notation, we use the J notation, where J now represents the square root of -1. And as long as we're going to represent that, we have to give some meaning to that letter J. And that meaning for our system in electronics is a plus J stands for 90-degree angle, and a minus J represents a minus 90-degree angle. So basically, you've got plus J upwards, minus J downwards as your y-axis. But if you notice also that if you square J squared is equal to -1. So if you have a number, a number b, and multiplied by J squared, then the answer is actually -b, a real number, -b. But to give some further meaning to it, We know that sinusoidal waveforms are equivalent to, if they're opposite one another, they're 180 degrees apart. 180 degrees then represents a j squared. So the j squared implies that there's a 180-degree phase change. So we can create a little table here to show what is meant by angles and j's. If you have a 0, that's you use basically, it's a real number, so you multiply the number by 1. If it's 90, it's basically a number that's 90 degrees apart from a real number or a j number. If it's 180, we said j squared represents 180, so that's basically the opposite, -1. And 270 is, well, j squared we said was -1 times j, so 270 is represented by minus j. And 360 gets us back to 0 degrees again. So we can use the Cartesian coordinate system in x and y, but we call them as both the real axis and the x, and the complex axis and the y, or plus j and minus j. Real is a resistance, plus j can be either XL or VL, inductive quantities. Minus j can be either XC or VC quantities, capacitive quantities. Okay, but the plus or the minus really depends on which variable you're using. Is current leading voltage, or is voltage leading current? That kind of thing. So if we first want to use complex numbers to define an impedance. You know the impedance value, what normally is the square root of r squared plus the square of the reactivate component. Here in this case, we're just going to make it a linear equation to say, look, you've got a real part and an imaginary part, because there's a 90-degree difference between the two. In this case, for a resistor in series with an inductor, we've got a plus J4, so it's 3 real plus J4 imaginary, plus because of the 90 degrees, plus 90 degrees. If it's capacitive, then the impedance is 3 minus J4, okay? Minus J4, because it's capacitive. Okay, if we have currents now, the current phasors are, you remember, if you have parallel situations, you use current phasors. So we represent then the currents as complex numbers. So I total this, in this case, we got a 2 amp current going through a resistor, which is real, and a 5 amp reactive current going through the inductor. So our total current is 2 minus J5. It's minus J5 because the current actually lags in the case of an inductor. Okay, but in the case of a resistor, the current leads, so it's 2 plus J5. Okay, so for inductor, it's minus, and for capacitive, it's plus. And if we want total impedances, then we, if it's in series, we, just as we do, think of these as just resistors. If the resistors are in series, you just linearly add them up. If they're in parallel, then you reciprocally add them and we take the reciprocal. So if we have a series circuit here, 9 ohms, 18 ohms, 2 ohms, and 3 ohms, we got a ZT, which we add all the Z's. Okay, we got 9 real plus 18 inductive, or J18 inductive, minus 2 capacitive, and then finally another plus 3 real. So we combine the real parts, 9 and 3, to give us 12, and we combine the imaginary parts, 18 and minus 2, to get 16. So ZT is equal to 12 plus J16. We have it in parallel, and then we want to take the reciprocals of all each of these guys. So we take the reciprocal of 4, the reciprocal of J8. Now that J is involved in the reciprocal, and the reciprocal of J and 5 for the capacitive, okay? So we have to figure out a way, okay, how do we deal with reciprocals? And if we have a parallel series circuit, there's another circuit type, we can say, well, we've got 2 paths here, okay? We've got 2 Z's. Z1 is a combination of that resistor and that inductor, 9 and 5. So we've got Z1 branch, 9 plus J5. And in this case, we've got capacitive and resistor. We've Z2 that becomes 3 minus 2 J2. So then ZT, then we have to take the reciprocal of Z1 plus the reciprocal of Z2. And we don't know how to handle reciprocals yet. So let's play around with these and try to figure out, first of all, we know what the addition subtraction rules are. We add the reals together, and we add the imaginaries together when we, or subtract them, whether we're adding or subtracting. If we multiply an imaginary or a complex number by a whole number, then we multiply that whole number into by the real and the imaginary parts to get a higher complex number. We do the similarly thing. If we divide by a real number, we divide both the real and the imaginary parts by that number. If we've got 2 numbers that are imaginaries, JB and JD, okay, if we multiply those 2 together, you notice the J squared, you get a J squared, and you multiply the B and the D together to get some other product, but times J squared is minus 1, so it's the negative of the product of the numbers. And similarly, the division, dividing a J term by a J term, then the J's drop out to give you a real number. It's basically just D over B. So now let's multiply 2 complex numbers together. And basically it follows the same algebraic rule. You take the first number, multiply by the second combination, and then you take the second number of the first and multiply by that, add all like terms together to get, in this case, you get A times C minus B times D, and plus J, A times D, B times C. Okay, that's how you do that. Basically, it's the same way you normally do your algebra. Okay. Now at this point we're going to introduce the complex conjugate. Okay, complex conjugate is a number where we take the opposite direction of the complex portion of it. So if we have A plus JB, we get the conjugate as A minus JB. If this were A minus JB, then the complex conjugate would be A plus JB. So let's look and see what happens if you multiply a complex number by its complex conjugate. When you find out that you get basically a real number given by the square of the real portion added to the square of the imaginary portion of it. So you get a real number. If you had just a purely imaginary JB number, okay, we can write that as a number 0 plus JB, right? So it's 0 plus JB. And if you take the complex conjugate of 0 plus JB, is 0 minus JB. So finally, multiplying Z by its complex conjugate, you just get B squared. Okay, so it's basically you end up with the square of the imaginary number. All right, supposing we want to divide. Okay, if we want to divide, then we want basically, simple way to do that is to make sure that the denominator is essentially becomes a real number. So when we have a numerator divided by a denominator, then we can take the denominator, and if we multiply the denominator by its complex conjugate, we'll get a real number, okay? But if we do that, we also have to multiply the numerator by the complex conjugate as well. So if we got Z1 divided by Z2, we take Z1 times the complex conjugate of Z2, and then divided that by Z2 times its complex conjugate. So we get Z1 times the complex conjugate of Z2 divided by C squared plus D squared, okay? The result would be a complex number divided by a real number. So basically we're going to apply that to this problem here that we tried to solve earlier, okay? Where now Z total is going to be equal to the reciprocal of additions of each of these. So we take 4, the reciprocal of 4 is 0.25, the reciprocal of J8 is minus 0.125, take the reciprocal of number times J, okay, and add the reciprocal of 5, which is 0.2, so we add these two together, okay? So we get 0.25 plus, 0.075, which is the difference between 0.2 and 0.125, okay? So we've got to take then the reciprocal of this number. How do we do that? The reciprocal is 1 over the complex number. Okay, so now we're going to use a conjugate method. Is we multiply 1 by the complex conjugate, so it'd be 0.25 minus J 0.075 divided by now the square of the real and the square of the imaginary portions. So we get 0.025 plus J, there should be a J 0.075 of 0.068 divided by 0.068. And then we divide 0.068 to 0.25 to get 3.67, and we divide 0.068 into 75 to get 1.1. So then we get, if you take, to get Z, then the value of Z total, then we get 3.6 squared plus 1.1 squared, and take the square root of that to get 3.83. And then the arctangent of minus 1.1 over 3.6 gives us an angle of minus 16.7 degrees. So meaning if it's a negative, we know it's mainly capacitive. Okay. So we can do the same thing by more complex wise. If we have Z1 and Z2 like we did before, and we simply have to figure out ZT as Z1 times Z2 over Z1 plus Z2. Z1 plus Z2 can be added in rectangular form, and the multiplication is also in rectangular form. So we can basically start out with Z1 and Z2, multiply those two guys together, and suppose we add and take the denominator as the added addition of these two. Then once we find the answers to that, we multiply by the numerator by the complex conjugate of the denominator, and the denominator times its complex conjugate to give us a real number on the denominator. And once we apply all of that math, we end up getting an answer of 1.79 real plus 1.09 imaginary, giving us for a magnitude of 2.1 and an angle of 31.34 degrees, meaning it's positive, so it's mostly inductive. So let's consider the reciprocal problem. So if you let xi equal j5, which is 0 plus jx, where x is a real number, let's find the reciprocal. So 1 over 0 plus jx, applying the complex conjugate like we did before, we get 1 minus 1 times 0 minus jx over the complex number combination. Okay, and we're left with 0 minus jx divided by x squared. So if we go through this, we find out that we get the answer as minus j 1 over x. So the reciprocal of jx is simply the negative j times the reciprocal of x. So the reciprocal of j5, is minus j 1/5 or 0.2. Okay, so there's our rules. We've got our different rules. So what we've done so far is rectangular coordinates, which have a real part and an imaginary part. So z is equal to real plus j times the imaginary portion. Okay, so we're going to go from rectangular coordinates to polar coordinates. Okay, if you remember, polar coordinates are basically coordinates that use a magnitude and an angle. So polar coordinates have magnitude and an angle, and it's given by z is equal to a as a magnitude, and that stands for the angle. And angle theta is a phase angle. And the magnitude of A, we know, is the square root of the real squared plus the imaginary squared. The theta is determined from the arctangent of the imaginary portion divided by the real portion. Okay, those are all the rules we need. So how do we convert from rectangular to polar examples? Well, if we have 2 plus j4, the real is the 2, and the imaginary is the 4. The magnitude is square root of 2 squared plus 4 squared, giving us 4.47. And the angle is the arctangent of 2 over 4, giving us 63.47, and so forth. And you can do the same for the rest of the things. And basically, it's very easy if you set this up in a spreadsheet, because you just have to put down the numbers here, figure out what the math is for here, the magnitude and degrees, and then replicate them down so you get them all. You enter the real imaginary numbers and then evaluate the magnitude by the Pythagorean theorem and the radian angle from angular imaginary over real. Okay. If you want to use, you'll want to use, when you're using this in an exam or so, you'll want to use your TI-30. Okay. This just tells you how to do it. So basic, from rectangular to polar, that stands for. Rectangular to polar. So in the case, get magnitude, you want rectangular to polar, or you want to go to rectangular to angle to get the magnitude, and to get the angle, you use the second portion of it. All right. Graphically, okay, we see that we have a number here, which 2 plus j4. Okay, let's say 2 plus j4, that could be current, or it could be a impedance. Okay, we know that the angle then, if it's 2 and 4, we've said that it's the arctangent of 2 over 4 is 63.43 degrees. And the length, we said the length of 2 squared plus 4 squared taken square root is 4.47. So it looks like a vector or a phasor. You know, it looks like both. Okay, the math is the same. That's the important thing. What about a negative angle? Well, you got A minus J6. So right away, you see the minus there. You know that that's a negative angle. It's basically in the 4th quadrant. So you do that. This is what you do that. If you do that using your calculator, you come out with a magnitude of 10 between the 8 and the 6, magnitude of 10. And then if you figure out the angle using this process, you come out with minus 36.86, because you're taking the arctangent of minus 6 over 8. Okay? So, and you end up with graphically something that looks like that. Okay? So if you have to draw a graph, this is what your, if it's a current, or if it's an impedance, that's what that looks like. So what's the significance of using polar values? Because they are a simple way of multiplying and dividing. So if we define Z1 as A with an angle theta 1 and Z2 as B angle theta 2, and if we multiply Z1 by Z2, we just simply multiply A and the B together to get the magnitude of Z1 times Z2. And then we add the two angles. Simply add the two angles. So this gives us an easier way of doing multiplication. Similarly, if we do division, we have A divided by B, and we subtract the angles. We take the B angle, subtract it from the A angle, okay, to get something new. Or we can just say if Z2 divided by 4 is basically B over 4, and the angle remains the same, okay? But if we take 10 and divide it by a polar number, so 10 has got an angle of 0, 10 has got an angle of 0, and A has an angle of theta 1, so we get 10 divided by A, but the angle is going to be 0 minus whatever the angle theta 1 is. So these are the rules. So from polar to rectangular, well, you know how to do that. Same. Real is A cosine theta, and imaginary is J A sine theta. So let's do a series circuit. We've got a 2 ohm and a 4 ohm resistor. We've got a 4 ohm inductor and a 12 ohm capacitor. And we want to determine if if the voltage we put in there is 20 degrees straight. So let's put it in, let's design it first. Our method's going to be figure out what's the total impedance, ZT. We do that in rectangular form. Then we want to convert ZT to polar coordinates. Why do we do that? Because it's easy it's the way to divide it. We divide it, it's easier than to figure out the complex conjugate and so forth. So we get, then our current IT is going to be VT polar, okay, which is 20 and at 0 degrees, and Z, whatever ZT polar is. And then once we've got IT, then we can also figure out all those different voltage drops. So ZT, we can do that arithmetically to get, we add all the resistor values, 2 and 4 to get 6. Then we've got 4 ohm inductance and a 12 ohm capacitance, giving us a net of 8 ohm capacitance. Okay, so ZT, then we convert, there's our rectangular form right there. 6 and 8 have a magnitude of 10, and the angle is minus 8 over 6, so it's the arctangent of minus 8 over 6, which is minus 53 degrees. So ZT is 10 with an angle of minus 53 degrees. I total is 20 degrees at 0, divided by 10 at minus 53. 10 into 20 is 2. Minus 53 subtracted from 0 is plus 53. So, and then we can combine them. We got 253, so we can multiply that to the resistor to get that, and we do the same for VL, VC, and VR2 to get all that information. So supposing we wanted to get equivalent impedances. Okay, what's the equivalent impedance We have a parallel circuit, which is 10 ohms, 10 ohm inductance and resistance 10 ohms. What would be the equivalent if we had made that into a series? Well, we have to find out what the total ZT is, okay? We do that, and we're doing this way. We're starting out with the complex conjugate, okay? And we turn the complex conjugate, or we can use the complex conjugates, and we use both the rectangular method and the polar method. Finally, the division is done by the polar method to get a 5 plus J5. Okay, if that's ZT, then we know that 5 ohms is the resistance, 5 ohms is XL. Okay. We can do the same thing using, remember, we call that the conductance G. G is in Siemens and reciprocal 1 over ohms, because it's simpler to add parallel currents than it is to use reciprocal resistance. So we can also do reactive admittance and susceptance. Admittance being Y, which is the opposite of impedance. So Y Siemens is equal to 1 over Z ohms. And the angle will change sign due to the reciprocal relationship. So if Z is 5 and 30 degrees, Y is 1 over 5 or 0.2 and minus 30 degrees. Susceptance, it basically is just another word as the opposite of reactance, and it represents 1 over X. B is in Siemens and X is in ohms. And basically this should, if you recall, this is a way of measuring currents, total currents running in the different branches. So let's suppose that we have a parallel impedance exercise here. We've got 6 and 8 ohms and 4 and 4 ohms, resistor, inductor, and resistor, capacitor. Parallel branches, 2 parallel branches. Z1 is 6 plus 8J, J8, and Z2 is 4 minus J4. Our total is Z1 plus Z1 times Z2 over Z1 plus Z2. 6 plus J8 is 10 by 53 degrees. 4 minus 4J is 5.66. And of course, it's minus 45 degrees because the real and imaginary are the same magnitude. So Z1 plus Z2, first of all, we can do that handily by just adding these two together. 6 and 4 are 10. 8 minus 4 is plus 4. So 10 plus J4, getting them into polar form, 10.77 and 21.8 degrees. So Z1 times Z2, we can do that simply by multiplying the two in polar form to get the answer at 10 times 5.66 at 53 degrees plus or minus 45 degrees, so we get 56.6 degrees. Now 56.6 at an 8 degree, because 8 degree between. Less 53 minus 45. Okay. Since Z1 plus Z2 is that in polar form, so now to get the total, we take the this number divided into that number to get the polar form number of that. And we can convert that to a real and an imaginary part, getting us back to a rectangular form, 5.08 minus j 1.27. All right. So suppose we wanted to add branch currents. So we got branch current I1 and branch current I2. I1 is 6 plus J6 current leads, right? And I2 is 3 plus J4 minus J4 current lags. Determine IT, the total current, and convert to polar form and what is Z equivalent. So I total is going to be equal I1 plus I2. So it's, take the rectangular numbers and add them together to get 9 plus J2. Okay, we add them in rectangular form, switch to polar form. We get 9.2 at 12.5 degrees. So we can't add in polar form, so we can't do it that way. We get Z equivalent is VA divided by the total current. Well, VA is 80 degrees at 0 degree phase, and ZT or IT is, we found out, was 9.2 at 12.5 degrees. Divide through, 9.2 into 80 gives us 8.7, and 12 degrees less, 12.5 degrees less 0 is minus 12.5 degrees. So we can, that's our polar form solution. Our rectangular solution then is going to be equal to this squared, well, by taking the cosine of 8.7 and the sine of 8.7 to get minus 12.5. Okay, so that is our rectangular form. And we can do it for more complex systems, okay? We can do it, in this case, we've got 3 different ones. We get 3 different currents, okay? And from 3 different currents, we can convert them all into polar coordinates. And so that's it. Okay. And you can do this. I will be giving you I can do this following the YouTube, or you can just follow the straight PowerPoint presentation.